Thank you, Roman. Thank you, Suki. Thank you, Tobias. Thank you, everybody, for being here. Like Romain said, I am Mathias VANWOLLEGHEM from IMN, and I will be talking about something very ambitious that we tried, mainly, trying to generate a CW Terahertz pure coherent source with a inverse pinhole emitter. So I put in the abstract actually a completely different title that was a bit arrogant, talking about the new paradigm and stuff like that. And I also added a big question mark to it, and you will probably see why. So, but first of all, let me underline the collaboration of all my colleagues in the lab. I mean, it's really a collaborative work. I shouldn't mention again Nicolas, Geoffrey, and Pierre. They have been mentioned already so many times. Let me really underline the presence of Jean-François. He's really the wizard in the lab when it comes to terahertz instrumentation. Guillaume and Stefano for helping us out with the receivers and the stable sources. There were very important people at the very first experiments in Grenoble who pushed us in really doing this. They are not from the Terahertz community or the Spintronic community, but they are from the ultra-stable community or from the spectroscopy community, like Marie-Aline Martin and Olivier Perali. And I should have mentioned also all my colleagues from the Nebula project for keeping us encouraging us to continue and try to do it, because it was really a tough work, and we really wanted to abandon it many times, but Romain, Suki, they kept on pushing us. So I was going to start by these slides telling where we're from, but I skipped those. But the only reason why I wanted to show that is to underline that I'm a bit humbled in front of this community of spin experts, because we are not at all from that domain. We are pure terahertz men, terahertz engineers, looking in big awe at all the amazing solid-state physics that you guys are presenting, and we are just trying to make applicative terahertz devices with it. So yeah, this is just to prove that these are our main thematics that we are researching in our team, and it's basically everything terahertz, but still focusing really on the device application and the system application. And me, Mathias here, I am not a spin physicist, so excuse me for that, and pardon my stupidities, if I say any stupidities about spin physics. So a few words about the terahertz range. This is the slide you all have seen 1 million times. Terahertz is where electronics and optics meet. It sits at 1 picosecond in time scale, at 300 micrometers in wavelength scale, 4 millieV in energy scale, and 49 K equivalent temperature. So they meet there, and it's been long time a gap. It was not possible to create a good source in it, but I mean, people worked very hard, and the electronics world tried to push their transistors up to a terahertz. They succeeded, but it was a really tough job. So Northrop Grumman demonstrated a couple of years ago a transistor amplifier at 1.2 terahertz. And we should give a big shout out to Jérôme Feist, who just got the Button Prize. It was just announced for all his amazing work in quantum cascade lasers. But also this was, I mean, a huge feat to get good CW terahertz quantum cascade lasers, and they're still quite limited due to phonon gaps and being not so tunable, and sadly enough, not operating at room temperature. But we could say that today lasers and transistors are able to oscillate at the same frequency. So Heinrich Rubens and Chandra Bose will be very happy, because that's what they've been trying to do at the end of the 19th century. But that's history. I'm not going back into that. But just shout out to a big German physicist who discovered the far infrared, Heinrich Rubens. So if it's that hard to directly generate it, can we do it in another way? So the most logical way is to do frequency conversion by using a nonlinearity effect. So just take a powerful source, look at the nonlinear phenomenon, and then multiply your frequencies, right? To get to the gaps where you weren't able to reach. That's what they've been doing in electronics. So VDI, one of the big companies in the domain, has been using varactor diodes to multiply microwave signals up to 2.4 terahertz. This is their latest product. This is a 2.4 terahertz mixer, but it has an efficiency that is horribly low logically. So it gets about almost 1 microwatt out of it at 2.4 terahertz, but you need to pump it with milliwatts of gigahertz signals. Coming from the laser world, from the optics world, yeah, well, you will all say, yeah, just take a nonlinear optics effect, and then you know that if you pump it with intense enough light, you will be able to create a polarization in your crystal, in your nonlinear crystal that can oscillate at some and different frequencies of the light that you're putting in. So you all know the lithium niobate work, where if you pump strong enough with an omega p and you seed it with an idler, then at the different frequency of the pump and the idler, you can get terahertz out. But still, yeah, there's a lot of problems there. You need to, it's a 3-photon problem, so you need to respect energy conservation, so you need to respect the Manley-Rowe. You have the Manley-Rowe limit, which basically tells you that the maximum efficiency that you can get out of your signal is the ratio with the energy of your the pump frequency. So nonlinear optics gives you horribly low fundamental theoretical limits. If every pump photon would generate a terahertz photon, of course it's worse than that because the Chi2 is weak. And you need to pump it even more, so your theoretical limit with Manley-Rowe, you never reach it. And what's even more horrible in nonlinear optics, well, horrible, makes it more complicated, is that because it's a 3-body problem, you also have to respect momentum conservation and momentum matching. So, I thought, so a lot of people thought in the terahertz community, nonlinear optics is maybe not the best way to generate terahertz CW. So can we do more easy frequency down conversion? Well, the most easy one is actually already discovered by Einstein, but he didn't realize it, or probably he did, but he didn't have the possibilities to do that. But in a way, when Einstein was studying the wave-particle duality of light, doing the photoelectric effect in 1905, he could have made a photomixer. Because when you look at it, if you shine a photon on the photocathode, and that photon has an energy that is a frequency that is higher than the work function of the metal, as you know, then it can get accelerated, and you put a potential between the photocathode and the anode. The electrons that are emitted, the free electrons that are emitted, are accelerating and create a current, a photocurrent. Now, if this photocurrent is basically proportional to the number of electrons per second, so proportional to the number of photons per second, given the quantum efficiency of the pump beam, of the photoelectric effect, and so basically proportional to the square of the electric field because of the particle wave duality, so proportional to the Poynting vector, and that's the simplest nonlinearity that you have. It's just a square of a field. So if this field is a 2-color field, then this phototube current would be oscillating at a different frequency of those 2 colors. So if the drift speed, if the transit time of the electron in this phototube is not too high, you could have a photoelectric mixer already at that time. Now you're going to laugh at this, or I don't hear anybody laughing, so you're probably convinced. But this is actually the very first photomixer. This is the paper of Forrester. Everybody always forgets this, but in 1947, Forrester at UCLA did the very first photomixing. And this is the very first time that the word photomixing appears in scientific literature. So what he did is he observed the beating of the Zeeman-splitted lines of a mercury lamp and just sent that into a photomultiplier tube. And then he looked at the beating current in that photomultiplier tube, and it beat it at 10 gigahertz. So, and he said in his abstract, in PR at that time, The basic idea is that in the photoelectric process, the emission probability for electrons is proportional to the square of the resultant electric field amplitude, implying an interference between light originating in an independent source. This is a point of view which does not appear to be tested in experiments involving quantum effects. So, and the experiment, this is nice, also demonstrates that any time delay between photon absorption and electron release must be significantly less than 10 to the minus 10 seconds. So he was already close to the picosecond there. So that's the very first photomixer in 1947, and then it took another 20 years before people started doing solid-state photomixing. That was, of course, in vacuum tubes. You had to put kilovolts on it. In the 60s, they started looking at creating photocurrents in semiconductors. So the first thing is Domenico did a lot of work in the 60s on cadmium selenide, and he was able to generate already at a few gigahertz using a Ruby laser a beating line of a couple of microwatts, but he still needed a lot of voltage to accelerate the free carriers. And of course, this is limited because of the lifetime of the carriers in cadmium selenide, who go up to a couple of nanoseconds. Then, in the 60s, there were the first fast diodes that were appearing, the germanium diodes, the first pin diodes. They also started doing mixing work on that, but there they were limited by the low mobility of the holes. So it took another 30 years to get really to the terahertz range. So photomixing is a thing that is possible. It's not nonlinear optics. You just need a very robust terahertz bandwidth fast photodetector. But apparently, people were not able to make them that fast. And then there were these two guys, Elliot Brown in UCLA and Tadao Ishibashi, who got a very simple idea to make the things faster. Elliot said just, well, in order to make the semiconductor faster, to have very fast photocurrents, we need to reduce the photocarrier lifetime below a picosecond. There's not a million ways to do that, but one way to do it is to make the photoconductor not as good a conductor anymore. So to put a lot of defects in it so that carriers that are generated recombine very fast. So he didn't invent low temperature grown gallium arsenide, but he was the first to have the idea to use that as a very fast photoconductor. Ishibashi took another approach. He said a pin diode can be fast, but the problem is it's limited by the low mobility of the holes. So we should get rid of the holes. And what Ishibashi did was he designed a band diagram, a band structure, that made sure that in the photodiode only the electrons would actually be contributing to the photocurrent, which are much faster. So in order to understand what the present-day photoconductors are able to do, and what we use all the time in terahertz community, I'm going to give you a couple of slides on that, and then see and tell you why we were so excited when we heard about the Spintronics, that we thought that, oh, they can help all the problems of the photomixers. So I don't need to explain this again. The LT gas is a very fast photoconductor, so you send a beating optical beam into it, and basically your carriers get very fast accelerated towards the electrodes. And these electrodes, these bias electrodes, can immediately also serve as an antenna, and you radiate your terahertz photocurrent. Your photocurrent that is oscillating at terahertz frequencies gets radiated by this antenna. That's the thing. So that's basically what I just said. The advantage is it's incredibly simple to fabricate. It's not nonlinear optics. There's free carriers here. So you don't need phase matching anymore. You have no more problems with low chi2. You have no phonons, the interaction length is better, you are not hindered by Manley-Rowe limitations. So the thing is, can be very efficient, it can operate at room temperature, and if you just vary your lasers by 10 nanometer in wavelength, you already get 5 terahertz around 800 nanometer. And the thing is, it's also true coherent CW. It's just the line width of the terahertz that comes out is basically the line width of the beating lasers. So, this is what I already said. The workhorse is really low temperature grown gallium arsenide, and it does what it does because by growing at a low temperature, you create a lot of defect states in the gap. The thing becomes semi-insulating, and the carrier lifetime goes down and drops to a couple of hundreds of femtoseconds. So if you bias then the thing, basically what you create here is a conduct. You You switch on the conductivity of this channel by sending a beating light into it. And the conductivity of this channel follows the beat of the line, right? So in practice, you do it like this. You interdigitate contacts on it. You connect this to a spiral antenna that will radiate the terahertz. The good thing about this contacts here, these interdigitated contacts, is that they have a very low capacitance. That's something to keep in mind. It's important to know. And then the bad thing is that, well, this whole thing only has a DC responsivity of a couple of milliamperes per watt. So that's the thing you pay. You pay for it because you want to make it faster. Well, you lose DC responsivity, of course. So that's the first photomixer that Brown did. That was basically the picture of his, no, this is a picture of his publication. The previous one was one that we did. And well, he did the simple experiment. He took two lasers at a different wavelength, measured the wavelength of the wave meter, and they were tunable. He mixed them together in a fiber and then shone the whole thing on this fast diode, and then analyzed with the bolometer the power that he detected as a function of this difference frequency between these two lasers. And he saw that he had about 10 microwatts at millimeter waves, but then it's quickly dropped with about 12 dB per octave going to the terahertz. But it was the first one to measure it, and but he was also the first one to know the power 4 roll-off. So every time you double the frequency, you get a power of 2 to the 4 less mixing power. Now, to understand that, it's not so complicated to understand. This is what we always do in the terahertz community. We make an equivalent electric circuit of it. Basically, the things behave as a conductivity that varies in time, right? The conductance of the photomixer follows the optical power that is entering the thing. So if you then bias it, the current will, well, we simplify it heavily, but the current will follow this conductivity behavior. Of course, the amplitude of this harmonic conductivity gets reduced, and it's reduced because of the carrier lifetime of your photoconductor. But if you then do some simple Kirchhoff laws and calculate a model, you can estimate what is the power coming out of this thing, and you will see that there is actually two characteristic times involved. There is the lifetime of the carriers, of course, but there's also a lifetime related to electric effects, because actually a photoconductor also gets capacitive effects once you start contacting it. I mean, there is charge buildup. So that's why I mentioned that capacitance was important. So you get an RC time constant that is also coming into play. Now, if we have this model, can we now estimate what a standard photoconductor does? A good one, the best one that we're able to make, right? So, and then I will be referring to one that we published, which we think is one of the best ones. So we take this model again of the estimated terahertz power that comes out. This is the model I showed you in the previous slide. Notice that it's proportional to the DC photocurrent, which in itself is, of course, proportional to the square of the DC photocurrent, which is proportional to the square of the incident DC power, the average power. So it's a nicely quadratic thing in P0, which is important to keep in mind. So if you now take typical values for all these parameters, so the typical conductivity, zero DC conductivity that you have is of this order, 1 over 180 ohms. The typical photocurrent is about 60 milliamps. The lifetime that you get is around a couple of hundred femtoseconds. So that means that the cutoff frequency due to the lifetime is 400 gigahertz. And the capacitance is measured around a couple of femtofarads. You get an RC cutoff frequency of 1.5 terahertz. And then if you send this thing into a matched load, so you make sure that your antenna that you connect to it has a conductivity that is close to the DC conductivity of your photoconductor, then so typical antennas can reach impedances of 100 ohms, so that's already close to the 180 ohm you have there. Then plugging this in, you get at around 300 gigahertz, you would get 600 microwatts photomixing, so true coherent CW. At 1.2 terahertz, with the 12 dB roll-off, you get 2 microwatts. These are actually measured as values that are predicted, and they were also measured, so the model fits. If you then further extract it to 4 terahertz, it really drops immediately below the 1 nanowatt. So you get this 12 dB roll-off, and there's no way that you can get rid of it. I mean, you can hope to make this, the 12 dB will always be there. You can only push away the frequency where the roll-off starts by playing with these lifetimes. But I mean, there's only so much you can do in gallium arsenide. And by playing with the RC time constant, but there's only so much you can do with the capacitance. I mean, 11 femtofarad is already incredibly low. So, but they're wonderful CW sources. They have, sadly enough, a steep roll-off around starting at 500 gigahertz. And something I didn't discuss here, actually, if you calculate this model and you also calculate the DC power that you send to do the thing, you will notice that there's only 60% of the DC power that actually gets transformed into terahertz. And that's the theoretical limit. So it means that more than 80% of the DC power gets transformed into heat. But in the Spintronic emitter, it's even worse. So we should be happy about the 80%. But still, it's an issue. I didn't discuss it here. It's an important issue to do when you design photomixers. But if you take, then all of this, so it was quite a long introduction, but just to tell you why we were so happy to see Spintronic emitters arrive. If we summarize a bit all of the zoology of DC photomixers that have been published in literatures and all the things that have been done. So I didn't talk about the UTC PDs. These are also very nice, but they have an even higher roll-off because they have 3 time constants involved. Didn't discuss that. If you take a look at all these optimizations that are possible, thermal management, resonant cavities, working on the capacitance, membrane emitters, the conclusion is always the same. They are very good at the low frequencies. They emit milliwatts or several milliwatts up to a terahertz, but then they kill. They immediately go towards the noise floor once you start approaching a couple of terahertz. So, can STEs save us here? And now, I'm very happy to be in front of this community. I don't have to re-explain all of this. You all know this perfectly well and much, much better than I do. As we've heard many times today, if you heat the thing up fast enough, you get ultra-fast demagnetization effects, as was demonstrated by the late Eric Beaurepaire, God have his soul. He demonstrated that for the first time in '96. And then Tobias got the great idea to make the spin channel, to create an even more efficient spin channel to be able to look at electrical dipole emissions by breaking the symmetry and adding another metal on top of a non-magnetic metal on top of the magnetic metal. And then taking advantage of this of the spin-orbit coupling in that non-magnetic metal, you have the spin-to-charge conversion phenomena, and finally the ultra-fast scattering in the metals make that this whole thing can be extremely broadband because all the timescales involved are of the order of 10 femtoseconds. So compared to the LT gas, we gain at least 1 order of magnitude on the timescales here. So, wonderful. I have a Spintronic emitter. I have a much faster photoconductor. I, as a terahertz man, I'm very happy. I will shine 2 lines on it and look at the beating of those 2 lines, and I will be able to go and make photomixing without any problem and a flat transfer function up to 10 terahertz, right? So I have a wonderful spin voltage biased photoconductor, right? Yeah, so credit where credit is due. Of course, there was much more work. Tom did all the amazing stuff to optimize the whole process and now make the most wonderful Spintronic emitters that we can all buy now. No, c'est pas vrai. Okay. And then, so he showed that we have this, behavior where the process is so broadband, but okay, right, I'm not going to make any enemies today. I'm still convinced that up to a couple of terahertz, there's nothing better than a photoconductive antenna. But of course, you get all these high frequency components. Right, so skipping this, I was going to do some shameless self-promotion about all the other work that we did. I said this already, so this was the idea that we had. So we can now use the Spintronic emitter to put us somewhere on the state-of-the-art diagram and reach this region, which was only accessible before by cryo-cooled QCLs, with their limitation that they are not working well at room temperature, that they have almost no tunability, and that they are very much hindered by phonon gaps. But and the roll-off would only kick in at above 10 terahertz. But we had no idea where we would be in amplitude here. So I'm putting this, but it could as well be that we're sitting here and that the difference only starts kicking off here. So this is what we had to do. So if we want to estimate whether we were able to do it, so the thing is now, the big difference with what you guys are doing and sending in the pulsed emission is that we are now harmonically pumping the thing with 2 lines. So if you are continuously harmonically pumping the emitter, would that cause a problem? We don't know. Tom explained to us that the times involved are still, well, there's electron phonon coupling also that interferes, that comes into play. So there's a time scale that is a bit worrying. The electron spin relaxation time is also a bit worrying. And then looking at the scaling work that has been published by, for instance, the Saraceno group, we saw that, well, still the intrinsic efficiency that you get, even in post-emission, is always not much better than 10 to the minus 6. So if we want to do it now with CW, is it so naive? Would it naively be just 2 beating lines at 1 watt, harmonically pumping the emitter to get 1 microwatt of CW terahertz power out of it? Well, we are not quite sure because, and this is where I should mention Henri, I don't know where he's hiding, he's there. We thought about this a long time, and then Henry, together with his PhD student Marius Drong, tried to do simulations for us to estimate what would be the ratio of a CW emission with respect to a pulsed emission if we're in the same average pumping regimes. And the strange thing is that according to the models that they develop and that they find also in their numerical simulations, there's some kind of behavior where up to 2 terahertz, this ratio is only 10 to the minus 7. So, which would mean that if you get in a pulsed experiment 1 microwatt of integrated power, you would only get less than a picowatt in a CW experiment. But according to the model, and this is still not completely understood, there might be an omega-2 behavior when you go to higher frequencies. And then it starts dropping off when you approach the momentum relaxation times. So it's not a simple matter of scaling. But the estimations that we make convinced us that, okay, it will be very hard to measure it. We will not be able to measure it with a bolometer because the NEP of a bolometer is just way too high. So we'll need to do a heterodyne detection to be able to measure this, to measure these sub-picowatt levels. And then also we need to take into account that Johnson noise comes into play. So if the Johnson noise is about minus 140 dBm per hertz, that's the noise floor of an electronic receiver system. So if we have to work at very low resolution bandwidths on our heterodyne receiver. The problem is if you take 2 standard DFB lasers that start mixing, they always have a natural line width of about 1 megahertz. So if you plug in the 1 megahertz to this, you add 60 dB of extra thermal noise. So you drown your expected photomixing signal that is only picowatt strong, right? So you would need highly stabilized lasers to be able to see it. That's what we thought. Or you need something else. You need, in your pulsed experiment, you need a pulse that is very much stabilized in repetition rate so that you have a frequency comb that you're sending into your emitter with very stable frequency lines in your comb, right? So the first thing we did is we did 2 DFB lasers, standard DFB lasers. We went to see Samir, who is expert in this. He built a feedback cavity, which is basically ultra-high finesse cavity, and he locked the DFB laser on this ultra-high finesse cavity. And by doing that, he's able to make DFB lasers with a line width of less than a hertz and almost no drift. It drifts about less than 20 hertz per minute. So we did that thing. We did that, stabilize them for these two lasers, send them in a standard electronic receiver setup. So here is the Spintronic emitter, so the best one that we could get from Tom. And then, there's a bunch of focusing optics, and we focus the whole thing on a subharmonic electronic receiver, which sits here. This is one that's optimized for 300 to 400 gigahertz, and it's fed with a low noise synthesizer that is multiplied as a local oscillator. And then we send this mixing product of these two things to an electrical spectrum analyzer, and then we look at it. So here's what the setup looks like. So there's a lot of electronics involved. Here's the electrical spectrum analyzer, the synthesizer. Here's the VDI receiver with the horn antenna. Here you can see the emitter and the two magnets. There were wire grid polarizers to make sure that we were really looking at the Spintronic emission, and we didn't see anything for days. We sent in, well, okay, now you see that we see anything, but this was after days or even a week of searching for a signal. We realigned the whole thing. We took a reference optical photoconductive antenna to see whether there was a problem with the receiver. Everything worked fine. And then, yeah, well, I don't know, some alignment trick. We saw this small bump getting out of the, the laser is almost dead, getting out of the spectrum. So as a reference, I put also what we get from a optical receiver, and you see that there's 8 orders of magnitude between them in exactly the same experiment. And it's even worse, because for the Toptica experiment, we used only 30 milliwatts of pumping power, and here we were using 250 milliwatts. But we were happy. We saw the first thing. We jumped of joy. We had a day left in the lab. We did a little bit more of measurements to make sure that we understood what was happening, to already make sure that, for instance, we turned the polarization, the polarizers, to make sure that we killed the effect. Sorry, I don't have this curve, but believe me, it's there. We saw that the line width is actually, there is not really a line width enhancement. You remember that I said that the lasers that we're beating had only a hertz line width, and that I'm plotting here 24 hertz. But that's actually the resolution of the electrical, it's due to the resolution of the spectrum analyzer. And then we varied the power. We saw that we had 25 dB of dynamic range, so we could taking the power of 2 law dependence in mind, we knew that we could at least decrease the power by an order of magnitude. So 10 dB less power is 20 dB less terahertz power. So we tried that, and that worked. So we get this nice, in a log-log scale, this nice square 2 law. But of course, we were not happy, because this is 50 femtowatts of terahertz coherent CW beating. So you would ridiculize yourself in the terahertz community if you show that as a terahertz CW source. So we thought, okay, well, it's an academic curiosity, but we can go a bit further. So we wanted to study more, and then we thought, okay, we need very stable laser lines that are beating, but the best way to do that is just doing the pulsed experiment again, and make sure that the lines that are in the spectrum of your pumping pulse are very stable, that there is almost no jitter, right? And if you have a good repetition rate, your lines in your spectrum might be very far apart, and you have more power per beating line. So basically what we're doing now is, we're basically doing what you guys are always doing, but we're not looking in the time domain anymore. We're looking immediately in the frequency domain. We don't do a time domain spectroscopy of the signal that comes out of the Spintronic emitter. So we look at the photomixing beating of all the spectral lines that are inside a frequency comb. Now, the setup is basically the same as the previous one, but with, instead of stabilized DFB laser or 2 stabilized DFB lasers, we take a Menlo mode-locked fiber laser with these specifications. we send the whole thing again towards the electrical receiver. And well, the principle of what is happening is, because it will look a bit bizarre with the curves that I will show you, is the spectrum of the mod-locked laser gets down converted to the terahertz by the inverse pinhole effect. So basically you are generating a terahertz frequency comb, but that can be very wide band. And then you mix it with a local oscillator that is very precise. And this mixing product, you get it back in the intermediate frequency domain. Now, if you look at it, what happens is by mixing this, you get half of the lines that are, well, part of the lines that are flipped over, that are mirrored. So in your IF domain, you will always see doublets of lines appearing. But that's because your local oscillator is sitting between a tooth of the frequency comb. So when we do that, we did that again. And all of a sudden, things started working better. Of course, we're in pulsed regime. We're not in CW regime anymore. So maybe that's also a reason why it worked better. But we saw really nicely, directly in the frequency domain, all the mixing lines coming out. So we're not doing any delay lines anymore. We're just sending the whole thing to electronic receivers. And we're basically characterizing precisely the spectrum of a spintronic emitter. So we played around with that. We played with the local oscillator to show that we can play around with these doublets. All of that worked very nicely as predicted. And with that first receiver, so that 300 gigahertz receiver, we were able to measure 40 Coulomb lines between 380 and 420. So I'm not giving the exact numbers here, but basically it gets down that we have almost a flat mixing over this whole range. Now, this is not really already a very wide range, so you could say, yeah, but a photoconductive antenna would also be quite flat in that range. And here you still see some difference in power, but that's due, of course, to conversion losses in the amplifier that we used. But when we compared it with the LiFi experiments that we did with the true DFB mixing, it was already improving, right? But we are not really, I haven't convinced you yet, of course, that there is no roll-off. And that was the real challenge, of course. Here I did it at 300 gigahertz, but are you sure that it's still flat, that's a flat uniform transfer function up to all these terahertz that are promised by the STE emitter? So we still had to do the electronic experiment, but we need another electronic receiver, one that operates at least 1 terahertz. So we got one from VDI. Actually, we bought one. And we started doing the experiments. And here you say, whoa, that's incredibly noisy. And that was something that was also very surprising to us. We were not happy. And then we started, we were almost unable to get the line out of it. So we're like, oh shit, the thing is actually, there is a roll-off where there shouldn't be. But then we started realizing that actually this line that was hardly getting out, it was not because of it was so weak, but because it got integrated, it was drifting all the time during our measurements. And the reason why it was drifting, and that's what we realized later, is that the Menlo laser that we have actually is not such a good one. The repetition rate of this Menlo laser, and that we saw afterwards, has sub-hertz variations of the repetition frequency. You will say, okay, sub-hertz variation of the repetition frequency is not so bad. But if you look at the 1000 harmonic of your mixing lines, then it gets awful because you have to multiply your f-rep of a hertz bit 1000, so you get drifts of your frequency comb in the terahertz domain of more than order of a kilohertz. And taking into account that we have to measure with very low RBWs, we cannot measure over big spans. Otherwise, the scan of the electrical spectrum analyzer would take too long. So that was why we were not able to see it. So very first conclusion, almost finished. What we demonstrated is Spintronic inverse pinhole photomixing has been demonstrated for the first time with pure continuous harmonic pumping with 2 stabilized DFBs. We had with 200 milliwatts harmonic pump, so with 3 picosecond period, a single pure terahertz line against many expectations of a mere 40 femtowatt. But there was a square 2 law nicely observed. So is this the record in least efficient but frequency stable narrow line terahertz source? Probably it is. And is it a mere academic curiosity? I don't think so. Because by doing the other experiments with the frequency comb, we now are convinced that we can have ultra-precise high harmonic down conversion of using an IC inverse spin Hall emitter up to 10 terahertz. At least that's what in a way your measurements predict. We have seen it already over up to 1 terahertz. So we demonstrated it over 700 gigahertz. We have already seen a 2-octave wide comb, but there have been stability issues. And the whole thing is still rather low in power. So can we make it better, more precise, more stable, and more powerful? That's the big issue. But here, this is the lines that we observed. And this is what normally a PCA would do. So we don't really see a roll-off, but there is some uncertainty there. So to make it better, you remember that the Menlo laser was actually, sorry Menlo, you make great products, but that one is probably not as great as you mentioned. So we bought another one from a Swiss company this time, a young Swiss company, startup from EPFL. They have a very, very stable laser, a very good laser. It's actually not so expensive, but it doesn't emit a lot of power. It's a very good one. Take a look into it. And the guy leading the company is a very nice guy. He's French. So, no, Florian will be able to help you out. And what we did was, okay, we had to amplify the thing because it only emitted 50 milliwatts on average power. And it's a 1550 source. It's not an 800 source. And we saw that by itself, the rep rate of this thing was already quite stable, but we wanted to make it even more stable. So in our whole photomixing setup, Pierre and Jean-François had did amazing work to stabilize this, to put an extra stabilization circuit around it, an electrical circuit. So this is a 1 gigahertz repetition rate. So you shine this on a gigahertz photodiode, and you look at the photocurrent around 1 gigahertz, and you mix it with a signal generator of 1 gigahertz to stabilize your rep rate of your laser, right? By just doing electronic stabilization. So here is what this looks like. It's a whole stack of electronic equipment. But in the end, this allowed us to stabilize it perfectly that we had a drift with this handmade circuit of only 40 hertz in 10 minutes. So we have 10 minutes to do well, in 10, you have 40 hertz drift, but in a second, you have almost no drift, right? At least compared with, you divide this by 3,600 or 360, so you have a much less drift than with the Menlo. So by doing that and actually locking the whole thing in that way, this is what we got. And now we're able to do scans. You see how nicely the lines now come out compared with the previous one. And now we were convinced that actually we do have the same conversion efficiency from 300 up to 1050 gigahertz. And these measurements, actually you don't really see it here, but this was over a complete measurement bandwidth of almost a gigahertz. And the thing didn't move. So we could quickly, nicely scan with a 100 hertz RBW, almost several hundred of kilohertz. So this measurement may have taken a minute, but these lines didn't move. So the whole thing was very stabilized. And so that made us very happy. But we still wanted to make, but it's still quite low power, right? So we're sitting at, minus 90 dBm, so we're sitting close to a picowatt, but we're still not there yet. So we want to make it even better, and that's the work, amazing work that my PhD student did. Pierre, he designed a resonating cavity to absorb almost 100% of the pump by adding basically a photonic crystal cavity based on a DBR mirror just behind the STE. And we measured. So this was, I said before I lied, I said that I never do TDS measurements. This is, of course, a TDS measurement. On the TDS, we saw that with this design, we have 2.5 increase in amplitude, peak to peak. So we can have, we expect 6 times increase in terahertz power. So we wanted to see that. And in order to see that, well, we just had another toy to play around. And well, one reason we had to use another laser is because the cavity was sadly designed not for 1550, but for 800. and the man here was operating at 50/50. But we have a TACOR now, which is an amazing laser source. It's a 10 gigahertz repetition TACOR repetition rate laser. It emits at 800 nanometer. It gives us pulses below 50 femtoseconds with more than a watt of average power. And it is stabilized by itself. And it has an extreme stability. It was so stable that when we did this whole electronic receiver measurements, we even saw in the photomixing the stabilization lines of the electronic circuit inside the TACOR coming out of the spectrum. So these are these satellites that are coming out. But, so we then measured with this one both the regular STEs and the ones enhanced by the photonic cavity. And, well, it's not very clear here, but we see for every frequency, if you would compare, the scales are not the same here. Here you were sitting below minus 95 dBm. Here we're above 90 dBm. So it improved as expected. But, so we have a wideband frequency comb demonstrated with a Spintronic emitter, but it's still not very powerful, and we haven't been able to do it with electronic receivers at 2.5 terahertz. We have a new one that has arrived by VDI just last week, so we'll start to do the photomixing at 2.5 terahertz, and so that's basically my conclusions. I'm sorry to, well, maybe I'm not sorry. Well, I'm sorry for myself. I don't know if you really care about true CW photomixing, but I think it will never be a true CW photomixer, an inverse pinhole emitter. It's just science fiction. You would need hundreds of watts of harmonic pumping. But another thing that we really should start thinking about is that you could potentially make a 7-octave wide terahertz frequency comb with it. For the moment, we have in that frequency comb around 2 picowatts per line. But there are ways, this is the only first proof of principle demonstration, there are ways, there's lots of low-hanging fruit, there are ways to boost this. We never went higher than 200 milliwatts up till now with this pumping in this frequency comb experiments. There is no terahertz antenna included yet to collect better. So I believe that we can hope for a 10 terahertz wide frequency comb with approximately a nanowatt per line. And then you really are getting close to what dual comb spectroscopy can do nowadays. And if you are able to demonstrate dual comb terahertz spectroscopy to spectroscopists over 10 terahertz, they will build a statue for you. I mean, this is, you know probably dual comb how it works, but it's basically, you can do spectroscopy without a delay line. You just take two combs that are slightly shifted in FREP and you scan the whole frequency band like this. So, did I explode my time? Is it what you expected, or you expected that?
Thank you, Mathias.